Hello and welcome back to Diksha Karnataka. Now it's time for me to discuss all one marker question from the chapter Moving Charges and Magnetism. If you have missed the rapid theory revision of this chapter, you can visit our channel. The link is given there. Also in our WhatsApp channel, the link is shared. So if you have missed it, don't forget to watch it. But obviously that is very critical, and after that you have to watch my one marker video. Upcoming video is the 2, 3 and 5 marker session of the same chapter, right? And if you are watching this video for the first time, don't forget to subscribe to our channel. For all your PUC and KCET needs, we will provide you comprehensive study for your KCET and PU board absolutely free. Now let's continue with this chapter. First question: a current I flows along the length of an infinitely long, straight, thin-walled pipe. Then the magnetic field at all points inside the pipe is same but not zero. At any point inside the pipe is zero only on the axis of the pipe, is different at different points inside the pipe. So everywhere, if you see the options, everywhere they are talking about the points inside the pipe. Now let us look into a pipe. How does a pipe looks like? Pipe is basically, correct that. So a pipe basically looks like this, right? This is a shape of a pipe. Now pipe is a thin walled pipe. Thin walled pipe means this wall itself is very thin, so inside part is hollow. Now this is a metal pipe and it is carrying some current, say I. Now it says that what will be the magnetic field inside the pipe. So for that, what we have to do, we have to construct an Amperian loop inside the pipe. Okay, Ampere's circuit law. So if you apply that Ampere's Amperian loop, so if you construct an Amperian loop, you have to see that according to Ampere's law, B dot dl equals to mu naught I, where I is the current enclosed inside the loop. So what is the current inside? All the currents are basically passing through this outside wall, right? No current is being passed through inside the wall. So that means the current enclosed over here is 0. So our right hand side is 0. Now dl cannot be 0. Why dl cannot be 0? dl is of real length. Okay, so if you take integration, you will get the circumference of this circle. So dl cannot be 0, but on your right hand side you are getting 0 because current enclosed inside this loop is basically 0. That means only one thing that can be 0, that is electric field, magnetic field. So magnetic field has to be 0 at any point inside the pipe is 0. Okay, it is similar to that of a conducting sphere. Okay, conducting sphere. Okay, electric field inside a conducting sphere is 0, or you can consider a shell. Okay, charged spherical shell, where we have already established that electric field inside the charged spherical shell is 0. So you can consider it to be the similar thing, where inside the charge enclosed was 0. That's why electric field was 0. Here current enclosed is 0. That's why magnetic field is 0. Now next question: when magnetic compass needle is carried nearby to a straight wire carrying current, then the straight wire causes a noticeable deflection in the compass needle. The alignment of the needle is tangential to an imaginary circle with the straight wire as its center and has a plane perpendicular to the wire. So if you are basically, let us understand the options one by one. So first we have a current carrying wire and you have a magnetic needle. Magnetic needle is like this. This is a very small compass kind of thing. Okay, a very small in shape. Okay, so it causes a noticeable deflection in the compass needle. So if you bring it closer to the wire, the needle will deflect. Why? Because there is a magnetic field due to this current carrying wire. right? So magnetic field due to current carrying wire, that magnetic field will affect the compass needle and it will be deflected. So option 1 is true. Now let's see, the alignment of the needle is tangential to an imaginary circle with the straight wire as its center and has a plane perpendicular to the wire. So if you see that basically if this is the wire, then the magnetic field lines will be circular in nature and it will be in the plane perpendicular to the wire, okay, and obviously it will align in the tangential direction. Yes, so the second statement is also correct. This thing we have studied in our class 10th, if you remember, magnetic effect of electric current. So in that chapter we have learned this thing, okay. This is not a something new that you are studying in class 12th, it is basically knowledge of your class 10th. So both option 1 and 2 are correct. So option C is correct in this question. So read the question carefully, and in case your knowledge seems to be little off, then try to remember some of the concepts from your class 10th. Now, if a current I is flowing in a straight wire parallel to positive x-axis and magnetic field is there along the positive y-axis, so what is current I? Current I is in the x-axis, okay, and magnetic field is in y-axis, okay. So this is x-axis and this is y-axis, okay. The wire experiences a force in negative x direction, the wire experiences a force negative y direction, the wire experiences a force in the negative z direction, the wire experiences a force in the positive z direction. Now let's see what is the force that is being experienced by a current carrying wire. So current carrying wire experiences a force I into L cross B, right? Bill sin theta, that was the expression for force. Now in this case we are writing it in vector form because we are interested in finding the direction of the force. So how can we find the direction of the force from the vector notation? So for that you have to recall some cross product property that you have learned in your PU1. Okay, when you are doing cross product of two vectors, okay, A cross B, how to find the direction? To find the direction, first we will start with the first vector, that is L vector. Now what is the direction of L vector? Direction of L vector is basically in the direction of the current, that is in this direction. So first you put your hand like this, that is the direction of the L vector. Now what is the second vector? Second vector is B. So you curl your finger towards the second vector. Okay, so this is how you find the cross product. Then your thumb will point in the direction of the cross product. So cross product between L vector, which is in this direction, L vector is in this direction, B vector is in this direction. So L cross B is basically an outward vector. Outward vector means it is in the direction of positive z axis. This is the z axis, right? The outside vector is z axis, so this will be z axis, so it will be in the direction of positive z axis, not negative. If it was into the paper, then it would have been negative z axis, okay. So obviously the answer is clear. When you are doing cross product, the resultant vector will be always perpendicular to both the vectors. That is the basic principle of cross product. If you forgot, cross product means perpendicular to both of them. So either it will be out of the page or it will be into the page based on the which order you are doing, right? So in this case it is in the positive z axis. A strong magnetic field is applied on a stationary electron, then the electron. So if the electron is stationary, okay, if the electron is stationary, then it will not experience any force, okay. It will not experience any force because V is 0. If V is 0, no force acts, so it will remain stationary. It will remain stationary. The radius of the circle described by a charged particle moving perpendicular to a uniform magnetic field depends on. So let's see, the radius of the circle described by a charged particle. So charged particle moving in a magnetic field, okay, it will move in a circular path. Okay, the radius of the circle described by a charged particle moving perpendicular to a uniform magnetic field depends on its mass only, its velocity only, both mass and velocity, neither mass nor velocity. So if you forget the expression, I tell you just briefly, mv square by r equals to q v b. So v, one of the v's gets cancelled, so r is equal to mv by qb. So it is proportional to mass, it is proportional to velocity. So it depends both on mass and velocity. So radius is proportional to mass and velocity. Okay, also inversely proportional to charge and magnetic field as well. They are not mentioned in this option, but mass and velocity are mentioned. So both, it depends both on both. Okay, next, the frequency of rotation of the charged particle in an uniform magnetic field is independent of velocity of the particle. Now frequency means what? Frequency means angular, it can be angular frequency, it can be f, opposite to that of the opposite to that of the time period, but we can consider any one of the frequency. Does not matter, both are related. Omega is equal to, if you are considering normal frequency, then it will be 2 pi f. So it is not super important. If you find angular frequency, that is also okay. Now what is, how to find angular frequency? So we have solved that r is equal to mv by qb. Okay, now you have to replace this v with another term. So v equals to r into omega. So if you substitute that in this equation, what you will get? R equals to m into r omega by qb. Okay, so you can write omega equals to qb r by m r cancels, and you get qb by m. So angular frequency or frequency, whatever you say, it depends on q, b and m. Okay, it does not depend on velocity of the particle. It does not depend on velocity of the particle. As you can see, no v is involved here, so it is independent of velocity of the particle. Okay, it depends on charge, it depends on mass, it depends on the strength of the magnetic field. Okay, these three quantities, they all depend, only velocity of the particle is independent. So option A is correct in this case. Which of the following statement is not true regarding Biot-Savart's law? So Biot-Savart's law, now we have to put more concentration. The magnetic field is proportional to the length of the current element. Yes, magnetic field is proportional. You have to remember that. Here we have to find not true. Not true is important. The magnetic field is proportional to the current through the current element. Yes, it is proportional to the current. The magnetic field is inversely proportional to the distance of the point. This is wrong. It is inversely proportional to the square of the distance, not the distance only. Okay, so this could be one of the possible answer. Now we will see the option D as well. The magnetic field is proportional to the sine of the angle between the current direction and the line joining the current element of the point. Yes, this is also correct statement. So this statement C is incorrect. So even though it appears to be correct, be careful, read very clearly the options, that here they have mentioned inversely but not inverse square. Okay, inversely with the distance, it will be inversely with the square of the distance. Okay, so that is small inaccuracy, so you have to be careful and answer properly. The value of permeability of free space is, so permeability of free space, we know that mu naught by 4 pi equals to 10 to the power of minus 7. So permeability will be 4 pi into 10 to the power of minus 7. So correct answer is 4 pi into 10 to the power of minus 7 Henry per meter. Okay, so this is also another unit. So this is the correct answer. Next, a long straight wire carrying a current induced magnetic induction at any place that is proportional to the distance from the wire So a long straight wire carrying current induced magnetic induction at any place. So in magnetic induction means it's producing magnetic field, okay, proportional to the distance from the wire, independent of the distance, inversely proportional to the distance from the wire. So basically this is the Biot-Savart's law, okay, it is inversely proportional to the square of the distance. So this is the correct answer. An electron is projected with uniform velocity along the axis of a current carrying long solenoid. Which of the following is true? So electron is projected uniform velocity along the axis. So electron is projected along the axis, okay, along the axis of a long solenoid. Okay, the electron will be accelerated through along its axis. Now if you see that the magnetic field inside the solenoid are basically constant and they are parallel, and it is parallel into the, this is a cross section of the solenoid. Obviously solenoid is very big. So if you consider a solenoid, suppose you consider a solenoid, the magnetic field inside the solenoid are parallel lines, okay. So if you project a electron which is passing through the axis, okay, the direction of velocity is parallel to the magnetic field. So if it is parallel to the magnetic field, it will not experience any force. If it will not experience any force, so that means there will be no acceleration as well, okay. So acceleration will be 0. Okay, electron will experience, will continue to move with the uniform velocity along the axis of the solenoid without any acceleration, without any circular motion. It will continue to move in the direction, and this will be the answer. If the beam of electrons and protons move parallel to each other in the same direction, then they attract each other, they repel each other, no reaction, neither attracts nor repel. Now very interesting question. Okay, electrons and protons static, they will attract definitely, okay, but what about electrons and protons move parallel to each other in same direction? So electrons moving in this direction, suppose protons are also moving in the same direction, okay. Now a moving electron, beam of electron can be considered a current flowing in this direction. So current is basically in the opposite direction of the electron flow. So electrons are flowing in this direction, right. So you can consider a corresponding current is flowing in the opposite direction. Now protons, if it is a beam of proton, you can say that this is also the direction of the current itself, okay. So here we can equivalently say, very important, understand this, we can equivalently say that the electron is basically representing a current in downward direction, proton is basically a current in the upward direction. So basically same direction moving electron and proton represents current in the opposite direction, okay. So they represents current in the opposite direction, or basically they represents anti-parallel currents. So anti-parallel currents, they repel each other, okay. So anti-parallel currents, they repel each other, so they will repel each other in this case. So even though electron and proton are oppositely charged, they will repel each other, because in this case the concept that is applicable is the attraction or repulsion between anti-parallel currents, okay. So static property is different, moving charges behave differently, very important, okay. Now next question. A rectangular coil carrying current is placed in a non-uniform magnetic field. On the coil, the total force is non-zero, force is 0, torque is 0, none of this. Let's see. Rectangular coil carrying current is placed in a non-uniform magnetic field, okay. Non-uniform magnetic field means the magnetic field is not constant, okay. So it will have some magnetic field, okay. So what will happen, it will definitely experience a torque will be there, okay. But the net force acting on this will not be 0, okay. Torque is not 0, Okay, torque is not 0 obviously. If you consider a rectangular coil placed in a magnetic field, it experiences a torque. Okay, it experiences a torque, right? We have seen that in my theory section. So torque is not 0, but if the magnetic field is uniform, force acting on this will be 0. Okay, similar concept that we have learned in the dipole and electric field, same concept. Okay, in case of dipole also we have learned that if the electric field is uniform, dipole experiences only torque, no net force. In this case, in non-uniform magnetic field, that means force is not 0, force is non-zero. Next question, a conducting circular loop of radius small r carries a constant current I. It is placed in a uniform magnetic field B, okay, such that B is perpendicular to the plane of the loop. The magnetic force acting on the loop is. So if you see that B and the loop are perpendicular, that means there will be no force acting on this loop. Okay, so B is perpendicular to the plane of the loop. So plane of the loop means the magnetic field due to the current carrying loop and the magnetic field, they cancel each other, so there will be no force acting on this. So the net force acting on this case will be 0. Next, in a moving coil galvanometer, the deflection phi on the scale by a pointer attached to the spring is. So what was the expression for the phi? Phi was galvanometer constant into I. So what is galvanometer constant? If you remember, NAB divided by K into I. So that's why I asked you to remember this simple formula. Okay, NAB by K into I. So the expression is NAB by K into I. So option C is correct. Even though this is very simple formula to remember, if you don't remember, if there is an MCQ question based on this, you will not be able to answer that. Resistance of an ideal ammeter is 0. Okay. A charged particle moves in a gravity-free space without change in its velocity. Which one of the following is not possible? So let us understand this. So charged particle is moving in a space, some space. Okay, so it may have electric field, it may have magnetic field. Okay, it may have both. Okay, it may not have anything. So a charged particle moves in a gravity-free space without change in its velocity. Which of the following is not possible? So you have to identify which of them is not possible. Let's see which of them are possible first. So if it is moving in a charged zone in a particular without change in its velocity. Without change in its velocity means it is continue to move in a straight line path. It is continue to move in a straight line path. So which of them is possible? No field is present. Electric field, magnetic field, both are absent. That means E equals to 0, B equals to 0. No force acts on this. It will continue to move in a straight line. Definitely this is possible. Okay, now let's see the second option. Electric field is not 0, magnetic field is 0. So if electric field is not 0, it will experience a force. If electric field is not 0, it will experience a force. Okay, does not matter magnetic field is 0 or not. Okay, so electric field is not 0 is not possible. Along with this combination, electric field is not 0, magnetic field is 0 is not possible. Why? Because it's a charge, right? So charge will experience a force. Now you might say, sir, okay, what about electric field? Suppose electric field is also in the motion of the charge. So charge will continue to move in the direction, but yes, it will move in the same direction, but it will start accelerate. Okay, it will accelerate in this direction because of the electric force acting on it. F is equal to Q into E. That will act on the charge and it will start accelerating. So that's why this case is not possible. So this is the correct answer. Now you can check the other two options as well. Electric field is 0. So no electric force acting. magnetic field is not zero. Now in this case you can say that, okay, if magnetic field is in the direction of the motion or in the opposite direction of the motion, in both cases it is parallel or anti-parallel. So even though magnetic field is not zero, the charge can still move with the same velocity, because in parallel and anti-parallel case, non-zero magnetic field will have no effect on the charge, because the force will be zero. Okay, so this is possible only when magnetic field is parallel and anti-parallel. No special case is mentioned. So even if magnetic field is not zero, if one of these cases is there, then it is still possible. So only possible or not you have to check. Now electric field is not zero, magnetic field is also not zero. So is it possible? Yes. We know that electric force is Q into E, magnetic force is QV B sin theta. So if electric force and magnetic force both non-zero and they cancel each other, electric field force is acting on, say, right hand side, magnetic force is acting on the left hand side. So in that particular case, electric force and magnetic force, they will cancel each other, so it will continue to move in the same velocity. So this is also possible. So these three cases are possible, this one is not possible. Okay. Now let's move on to the next question. A positive charge is moving in a combined gravitational and magnetic field. The charge moves without any change in its velocity. If the velocity of the charge is along the east, then the direction of the magnetic field is along. We have to draw a diagram. Okay. Positive charge is moving in a combined gravitational and magnetic field. So we have gravitational field. Gravitational field means there will be an mg acting downward, okay, and magnetic field, the charge moves without any change in its velocity. Okay, if the velocity of the charge is along the east, so charge is moving in the east direction, gravitational force is acting on the downward direction. Okay, so then the direction of magnetic field. So direction of magnetic field you have to find. How to do that? This is east. Okay, this is east. This is down, by the way. Okay, this is east. This is west. Okay, and if you consider this, okay, so east, west. So this will be north and this will be south. Okay, right. So you just consider in this direction, okay, because downward and upward is different. North, this is a three-dimensional figure. Now you have to understand, if this is weight mg, the magnetic force must balance this mg. Okay, only then the charge will continue to move in the same direction. These are the tricky questions. The questions from this chapter are little tricky, so you have to practice little bit more. Okay, understand this. So this is the upward force. These two forces must balance each other. Now when it is possible, so if you consider that, how can you get a upward force? So this is north, this is V. So is it possible? No. Why no? Because the magnetic force is given by Q V cross B. Now if you do V cross B, only if you see V and south, then only you will get an upward force. So only V cross B in the south direction will give you an upward force. So it will be in the south direction. So the magnetic field will be in the south direction. It will be little bit diagram related question. So try to draw the diagram if possible in such questions. Now let's move on to the next question. Question number 18. A charge Q mass m is moving in uniform circular motion under action of a magnetic field B. If the radius of the circle is capital R, then the magnetic moment associated with the charge is given by. So let's see. Charge Q, mass m is moving in uniform circular motion under the action of magnetic field B. If the radius of the circle is capital R, then the magnetic moment associated with the charge is given. How to calculate magnetic moment? Sir, I don't get this question. Charge Q, moving M, magnetic field B. This is slightly higher order thinking level question. So magnetic moment is given by I into A. Okay, I into A, current into area. Now what is current over here? That is very important point to understand. Current is basically charge divided by time. Okay, now if you see any of the options does not have time, so you have to figure that out. What is A, by the way? A is the area, so area is pi r square. Okay, so pi r square is the area. Now time is not given, so what we can do about that? So for that, what we have to do, we have to figure something out. We know that in circular motion, it is given by the motion is given by mv square by r is equal to qvb, right? qvb. So from there we can find velocity. Velocity is given by qb r by m. This is velocity. Okay, now if you know velocity, you can find something. So velocity is basically when it is rotating in the circular path. Okay, this is the angular velocity. Okay, so angular velocity will be r into omega. So that will be qb r by m. So omega equals to qb by m. Okay, so qb by m is the angular velocity. Now what is angular velocity? Angular velocity is the time it takes to rotate one complete rotation, right? Or the angle that it rotates, right? Distance divided by time is velocity, angle divided by time is the angular velocity, right? Now, so from there we can say that now to complete one rotation, if the time taken by it, say t, if time taken by it to complete one complete rotation is t, then how much angle it covers in one complete rotation? To complete one rotation, it covers pi plus pi, that is 2 pi. So omega can be written as 2 pi by t. Okay, so to complete one rotation, how much time it takes? It will take t equals to 2 pi by omega. Okay, so from here if you put the value, you will get time t equals to 2 pi by qb into m. Now you have to substitute this value in this equation. So you get this as q pi r square divided by 2 pi m into qb. So pi cancels and you get this as. It's a very interesting question, slightly higher difficulty level definitely. Q square r square b by 2m. So q square r square b by 2m, option C is correct. Okay, this question is taken from your question bank if you are wondering, right? Statement 1, a current carrying wire is placed parallel to the magnetic field. The force on it due to the magnetic field is 0. Okay, current carrying wire is placed parallel to the magnetic field. So current carrying wire placed parallel to the magnetic field. So what is the formula? BIL sin theta. Okay, so if this is parallel, that means theta equals to 0, that means force is 0. The net charge on the current wire is 0. Net charge on the current wire is 0, that we have learned in the previous chapter, that even if it is carrying some current, the net charge will still remain 0, only the electric field will be there, but net charge will still be 0. So this statement is also correct, but is there any relationship between this statement and this statement? There is no such relation between statement 1 and statement 2, even though both statements are true, but statement 2 is not a correct explanation of the statement 1. The correct explanation is this one, BIL sin theta is 0, that's why the force is 0. Match the physical quantities of column 1 with their units in column 2. Now in this case, as I said, whenever you are doing a matching question, you have to check which one you know first. Okay, you may know some of them, you may not know some of them. So which one of all of them you know, first you mark them. Okay, then you decide whether you can answer the question or not. Current sensitivity is division per ampere. Okay, current sensitivity is division per ampere. So this is correct unit for option 1. So option 1 is C. Okay, sensitivity means how sensitive is the device. So if you pass a 1 ampere current, how much division it will move, that is the sensitivity of the device. Intensity of magnetic field. Now intensity of magnetic field you may not know. Let's see the other option. Magnetic dipole moment. Magnetic dipole moment is what? Magnetic dipole moment is, I already told you the unit during my lecture, is current into A. So it is ampere meter square. Okay, A is area is meter square, I is ampere, so ampere meter square is the current magnetic dipole moment. So from there we can see that option 3 is matching with B, so definitely 2 will match with A. Okay, so CAB, so option B is correct, CAB. So whenever you see a matching question, try to figure out which one you can answer, which one you can match directly. Ignore the ones which you don't know. Okay, so that will automatically be matched. Next, an ammeter and a milliammeter are converted from identical galvanometers. Which one has the smaller resistance? Okay, milliammeter means it is measuring smaller currents, so it will have a higher resistance compared to a ammeter. Ammeter is measuring higher currents, so it must have a very small resistance. So ammeter will have a smaller resistance. Milliammeter, even though it's measuring smaller current, its resistance is higher. Current and resistance are always inversely proportional. Okay, V is equal to IR. So if current is high, then resistance has to be small. If current is small, resistance has to be high, V assuming constant. Okay, so milliammeter will have higher resistance, ammeter will have a lower resistance. Another matching question, the physical quantities related to magnetism are listed in column 1 and the dimensions are listed in column 2. Identify the correct match. Now let's see one by one. Now magnetic field, there are a lot of different ways to do the matching. We will start with our known first, magnetic moment. Okay, what is magnetic moment? Magnetic moment is the easiest dimension. Magnetic moment is I into A, that is dimension of current is A, dimension of M is L square, so AL square is the dimension of magnetic moment. So we can identify that from there. Which one is the magnetic moment? Magnetic moment is this one, B. Okay, so magnetic moment is B. So if you see that there are two options which is matching with option B. So sorry. So there is only one option which is matching with 3B. Okay, so only one option. So even if you don't know the rest of the matching, you can still answer it. Okay, that is the beauty of matching. Now there is one advice. Magnetic permeability is generally difficult quantity than magnetic field. So from here if you see that both quantities are almost same, but this has a 10 to the a to the power of minus 2, this one has a to the power of minus 1. So magnetic permeability is a to the power of minus 2 and magnetic field is a to the power of minus 1. Both quantities otherwise same dimension are. One more thing, length is not there in magnetic field, length is there in magnetic permeability. That is the major difference. Okay, so from there also you can match it, but even if you don't know the answer, only one correct match sometimes can give you the correct answer. So you have to be smart and don't always take hopelessness. Okay, I cannot answer this question. You may be able to answer questions if you pay a little bit more attention. Now next question. A charged particle of Q is moving in an uniform magnetic field. The angle between the velocity v of the charged particle and magnetic field B is theta. The trajectory of the charged particle varies with angle theta. Match the following table by choosing the appropriate trajectory traced by the charged particle for different possible values of angle theta. Now angle 0 means it will be a straight line, so 0 is straight line, 45 degree ignore it, 90 degree it will be circle, so 45 degree must be its helix. So if you have followed my lecture, any angle between 0 and 90 it will be an helix. 0 means straight line and 90 means circular path. So 1 is matching with B, okay, 2 is matching with C and 3 is matching with A. So 3 is matching with A, 1 is matching with B, 1B, 3 is 3A, 1B, 3A. So this is the correct matching. 2C automatically will match, right? So this is the correct matching. Next question. The Lorentz force is the force on a charged particle moving in a region containing only electric field, only magnetic field, both electric and magnetic field. Straight away from the definition, force on a charged particle moving in a magnetic field is maximum when the angle between the velocity of the charge and the magnetic field is, okay. So QVV sin theta. So sin theta is maximum when theta is 90 degrees. So force is maximum at angle 90 degrees. A charged particle is released from the rest at a region of uniform magnetic and electric field parallel to each other. The particle will move in a helix, circle, straight line, cycloid. Let's see. Charged particle is released from the rest at a region of uniform magnetic and electric field parallel to each other. So electric and magnetic field, they are parallel, okay, and you released a charge Q. So charge released means it is static. Initially it is static. Now when it is moving in the electric field, it will experience a force in the direction of electric field. So it will start accelerate in the direction of electric field. Now magnetic field is also in the same direction, electric and magnetic field in the same direction. Now in this case the angle between velocity vector and magnetic field vector will be 0. So 0 means no magnetic force will act, so it will move in a straight line. It will move in a straight line due to only electric field. Magnetic field will have no effect in this, so only straight line motion is possible here. A galvanometer can be converted into a voltmeter by connecting high resistance in series, right? Next, the dimension of magnetic moment LA square, we have seen that, so magnetic moment is LA square. Parallel currents dash and anti-parallel currents dash. So parallel currents attract and anti-parallel currents repel. A planar loop carrying a current I having n closely wound turns and an area A possesses a magnetic moment M, where M equals to, so we have done that, we have seen that. So magnetic moment M is equal to number of turns into I into A. NIA, National Investigative Agency. This is the magnetic moment of a circular coil, right? So this is the answer for this question. Now fill in the blanks. Let's solve 5 fill in the blanks quickly. When the charged particles move in a combined magnetic and electric field, then the force acting on it is known as Lorentz force. Lorentz force. Okay. Mark it. Next, the direction of the magnetic field due to a current loop is found using the direction of magnetic field due to a current loop is found. Direction of magnetic field due to a current loop, you have to use your right hand thumb rule. You have to use your right hand thumb rule. Okay, this is the direction. If this is the correct direction of current, this is the direction of magnetic field. The alternative form of Biot-Savart's law. Now this is very interesting. Biot-Savart's law and Ampere's circuital law, both are basically same laws. Just application wise different, but it is same. Ampere circuital law and Biot-Savart's law, both are basically same. That's why they are alternative form. Current carrying circular coil is equivalent to a magnetic dipole. Magnetic dipole. Resistance of an ideal voltmeter is infinity. Resistance of ideal voltmeter is infinity. Ideal ammeter is 0. So with this is the end. We are going to discuss all 2, 3 and 5 marker questions from this chapter. I have already discussed quick revision of the chapter and all the important 1 marker questions. 1 marker questions are many of them are very tricky and maybe difficult for you to answer. So don't forget to watch the 1 marker video of this chapter. So that will be very, very interesting and important. Now let us continue with the 2, 3 and 5 marker questions. If you have seen all the previous 2 videos, then it is also a must watch. Don't go anywhere, watch till the end. All the questions that I am going to discuss are very important. But before I start, let me give you a idea about what are all the questions that I am going to discuss. So I am going to discuss 5 2 marker questions. I am also going to discuss 6 3 marker questions and 4 5 marker derivation or long answer type questions. There will be no numericals, 5 marker numericals from this question. There may be some 2 or 3 marker numericals may come from this chapter, but no long form 5 marker numerical generally comes from this chapter. If in your midterm, if you get a 5 marker question, that will be easier question, because difficult 5 marker level questions are not possible from this chapter in general. That's why it is not there in the blueprint as well. So that's why I have only kept 5 marker long answer type questions, no numericals. Even you don't need to practice numericals from this chapter, except for 2 and 3 marker, which are I believe is easier, and if you are preparing for any competitive exams, those level of questions you should be able to answer anyway. Now let's start with the question. First question: when does a current carrying conductor placed in a uniform magnetic field experience maximum force and minimum force? So here we are talking about maximum and minimum force. What about who is experiencing that force? The current carrying conductor is experiencing a force. So what is the force on a current carrying conductor? The force on a current carrying conductor is simple: BIL sin theta. Right? So force will be maximum when theta equals to 90 degrees, and force will be minimum when theta equals to 0 degrees. Okay, 0 degrees or even 180 degrees you can consider. So 0 degree or 180 degree both are same, but it will be maximum when theta equals to 90 degrees. So this is the condition for maximum and minimum force. So you have to answer them and you will get full marks. Now next, a long air core solenoid of 1000 turns per unit length carries a current of 2 ampere. Calculate the magnetic field at the midpoint of the axis. So a solenoid having number of turns 1000, current is 2 ampere. So you have to find the magnetic field. So this is the formula for magnetic field at the core, at the center of the solenoid. Now mu naught, value of mu naught, you have to remember, mu naught by 4 pi equals to 10 to the power of minus 7. So mu naught will be equals to 4 pi into 10 to the power of minus 7 SI units. Okay, you do not need to remember exact unit. If you can remember, very good, otherwise SI units is sufficient. Okay, now B is mu naught Ni, so let's put the value 4 pi into 10 to the power of minus 7. Number of turns per unit length is 1000, which is given itself, and the current is given as 2 ampere, so multiply by 2. So now simplify it, you will get 8 pi into 10 to the power of minus 7 plus 3 minus 4. So 8 pi into 10 to the power of minus 4, and unit of magnetic field is Tesla, so it will be Tesla, right? So answer is 8 pi into 10 to the power of minus 4 Tesla. Very simple, easy 2 marker numerical question. Next question, a moving coil galvanometer gives a deflection of 10 divisions when 200 microampere of current is passed through it. Find the current sensitivity of the galvanometer. Current sensitivity means what? How much current is required for one division of deflection, right? So the current sensitivity is given by current divided by number of division. Okay, number of division, capital D. Okay, so current is here is 200 microampere and the division is 10 divisions. Very easy question, so it will be division. So the answer is obviously 20 microampere per division, right? So 20 microampere per division is the answer. Next, write the expression for the magnetic force per unit length between two long straight parallel conductors carrying current. Give the nature of the force between the two parallel conductors carrying current in the same direction. So here as you can see, this is the expression for force per unit length, force per unit length between two parallel current carrying conductor. This is the formula you have to remember. Parallel currents attract and anti-parallel current repel. So here only they have asked about parallel, but in case in the exam they ask about anti-parallel also, you can answer it from here. Parallel currents attract, anti-parallel currents repel each other. Now another question, a galvanometer has a resistance of 12 ohm and the meter shows a full scale deflection for a current of 3 milliampere. How will you convert it into a voltmeter of range 0 to 18 volts? So a galvanometer is there, the resistance of the galvanometer is given 12 ohm and the current that it can withstand is 3 milliampere. So 3 milliampere is the maximum current or the galvanometer current, that we denote it using the symbol Ig. So Ig is 3 milliampere. Now remember that we have to convert it into 0 to 18 volt. 0 to 18 volt means 0 obviously is not important, this 18 volt is important. So maximum when this much current passes through the galvanometer, it will give you a 18 volt reading. That is our target. Now to convert it, what we have to do, we have to consider that we have to there is a galvanometer and we are converting it into a voltmeter. So we have to definitely connect it to the external resistance of R in series. So galvanometer resistance is given 12 ohm, external resistance is R ohm. So what is the total resistance? Total resistance is 12 plus R, right? Now when the maximum current, that is 3 milliampere, is passing through the galvanometer, okay, the reading should be 18 volt. Okay, that's how we convert. Convert means even though 3 milliampere current is passing through it, the galvanometer will show 18 volt is the voltage, right? So for maximum current, maximum volt reading should come, right? So if this is the resistance, if this is the current, okay, then what is the voltage? V should be equals to IR. Okay, and V should be the maximum value here, 18. Ig is 3 milliampere and milliampere means 10 to the power of minus 3. That is very, very important. RT is 12 plus R, so multiply that. Okay, and now simplify. So you will get 3, 6 and it will come to other side. So r plus 12 equals to 6 into 10 to the power of 3. Minus 3 will come to the other side, become plus 3. So it will be 6000. So r will be 6000 minus 12, that is 5978, right? No, 88, 59888. That will be the resistance of the galvanometer. Now because this is a resistance, you have to add the unit, which is ohm. Very important. 5988 ohm is the required resistance. Now next question, state and explain Biot-Savart's law with a suitable diagram. So obviously you have to draw the diagram like this, and then you have to take some point P and join it, take some element, join it. The angle, you have to show the angle as well. So this is the direction, this is the angle theta, and then this is the length element dl. Current passing through is I. Okay, and then you have to mention that the magnetic field at this point due to this element dl is given by dl directly proportional to sorry, not dl, my mistake, the magnetic field dB is directly proportional to the length of the element. It is also proportional to the current that is passing through. It is also proportional to sine of the angle theta, inversely proportional to square of the distance, and combining all of them you can write dB equals to mu naught by 4 pi I dl sine theta by r square. Okay, the diagram is must, and then you have to write it. If you show everything in the diagram, you do not need to explain it, but if you are writing it in words, then you have to explain. Okay, next, derive an expression for angular frequency of revolution for a charged particle moving in a perpendicular to a uniform magnetic field. Or the same question can be asked as, obtain an expression for the radius of the circular path taken by a charged particle moving perpendicular to the uniform magnetic field. So first we will do this derivation, and once this derivation is done, from this derivation we will go back to the other derivation. So basically this is the easier derivation, and if this derivation is asked, that means you have to first do this derivation, and from there you have to go to the second part. Now obviously whenever a charged particle is moving under the influence of a magnetic field in a circular path, what force acts on it? The only force that acts on it is the centripetal force, and that centripetal force is provided by the magnetic force. So this is the radius, right? Now centripetal force acts towards the center, and the same force has to be provided by the magnetic force. So from there we can write that mv square by r, it is the centripetal force, okay, that must be equals to qvb. Now sine theta is equals to 1 because it's a circular motion. Circular motion means angle theta is 90 degrees. Now from here you can calculate the value of r. Now one of the v will be cancelled from both sides, and r will be coming out to be mv by qb. This is very simple derivation. This one is just one line derivation. You need to draw the diagram as well. Now also mention that the centripetal force must be equals to the magnetic force. That one line you have to write it. Okay. Next, what you have to do? Now we have to find the angular frequency. For angular frequency, what you have to do, that for angular frequency v equals to r omega, that is from rotational motion. So you have to substitute that in this equation, and you get as r equals to mr omega divided by qb. Now this r cancels, so you have 1 over here, and from there you get omega equals to qb by m. Okay, so this is the angular frequency. This is the expression for angular frequency, easy derivation. Next, what is Lorentz force? Write the expression and explain the term. So Lorentz force is when both magnetic and electric fields are present and a charged particle is moving under the influence of a magnetic and electric field. It experiences a force that is called Lorentz force, and its expression is given by, so when a charge particle moves under the influence of both electric and magnetic field, the force experienced by it is called Lorentz force. Okay, Lorentz is the name of a person. Okay, if you are wondering, so when a charged particle moves under the influence of both electric and magnetic field, the force experienced by the charged particle is called the Lorentz force. Okay, now what is the expression? Expression is given by F equals to Q into E vector plus V cross B, right? Next, how can a galvanometer be converted into a voltmeter? Explain with a diagram. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with it. So very simple, you have to take something like this and then a resistance. So this will be your galvanometer, and you have to cross it and you have to say this is the voltmeter. Voltmeter is combination of this G and R. How can a galvanometer be converted into an ammeter? Explain with diagram. A galvanometer is converted into an ammeter by connecting a suitable low resistance S in parallel called shunt with it, and the diagram you have to draw is this. Okay, and you have to mention this is the galvanometer. Also you have to show what is the current. If this current I passing through it, this is the Ig. Okay, so I, and this will be I minus Ig, right? So I G into G equals to I minus Ig into S. So this expression, if you draw it, it will be very, very helpful. Okay, now next, state Ampere's circuital law and arrive at the expression for magnetic field due to a long straight current carrying wire. Now statement of Ampere's circuital law is simple, that if you have a current carrying conductor and if you construct a loop around it, okay, then the magnetic field on the any point on the loop is given by B dot dl equals to mu naught I. So you have to write the statement in a proper way. I have given it in the theory portion of this lecture, and also if you want to download the PDF, this PDF and the PDF that for theory and MCQs, don't forget to join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Also, if you have not yet subscribed to our YouTube channel, don't forget to subscribe to our YouTube channel and share this lecture with your friends so that they can also learn and they can also score well in future. Now, so B dot dl equals to mu naught I. Now we have to find the magnetic field due to a straight current carrying wire, straight long current carrying wire. So we have to construct an Amperian loop like this. Say the distance of the point that where we are trying to find the magnetic field is say r, right? Now we have to construct an Amperian loop which is a circular in shape, circular shaped Amperian loop. You have to mention, let us construct a circular Amperian loop of radius r. Okay, then you have to apply this formula. Now you have to remember that due to symmetry B is constant at all points on the circle. Now direction will change, but the magnitude will be constant. So from there we can say that if there is a constant, that means it will come out of the integration. So it will come out of the integration, and what we have inside the integration is only dl equals to mu naught I. Now I is the current that is passing through this wire. Now what is the close integral dl means? Close integral dl means, dl integration means you cut a very long thing into small pieces and then you add them. Now dl means, dl here represents a small length dl. Okay, so dl is basically a small portion of this circle. Now if you take all such dls and add them, you will get the close integration of dls, and your starting point and your ending point has to be same. Then only you can write this close integration. Close integration means starting point and ending point are same, then it is called a close integration. And here close integration of a curve gives its perimeter. Close integration of a curve gives its perimeter. So in this case it will be the perimeter of the circle. Perimeter of a circle is given by the formula 2 pi r. So it will be nothing but b into 2 pi r equals to mu naught I, or b equals to mu naught by 2 pi I divided by r. Okay, so this is the expression for magnetic field. Okay, now next, derive the expression for the magnetic field at a point on the axis of a circular current loop. So this is the very common derivation, and it is coming almost every year. So let's do it. This is a 5 marker derivation. Previous one was a 3 marker derivation. Okay, here we have a current carrying loop. Here we have a straight line, and we are trying to find the magnetic field at this point P. You have to practice this derivation 2-3 times. Okay, don't make any mistakes so that teacher can deduct marks from the confirmed question or fixed question. You can consider this to be a fixed question. Okay, even for your midterm this question can be considered as a fixed question. Okay, there is a high chance that this question will come in your midterm exam. 90% chance is there. Okay, now what you have to do, first you take a small portion here, and obviously the radius is given by r and this distance is given by x. So you take a very small portion and you say, okay, what is the magnetic field due to this at this point? So this distance is given by say r, small r, then it will be square root of r square plus x square. Okay, because this distance r means this will also be r, right? So this is the right angle triangle. So right angle triangle, this is hypotenuse. Okay, now if you see there will be magnetic field at some direction like this, mutually perpendicular direction. Okay, and if this angle comes out to be theta, then this angle will also be theta. Okay, it can be proven geometrically. You don't need to do the geometrical proof of these two angles are equal. Only thing you have to remember that this angle theta means this angle will also be theta. Okay. Now if you consider this any point which is diametrically opposite. Diametrically opposite means, what is the meaning of diametrically opposite? If this is a circle, if you consider a point over here, this is the center. If you join the center and extend it, this is called a diametrically opposite point. For this point, this will be a diametrically opposite point. Okay, so each point on the circle will always have a point which is diametrically opposite, but it has to pass through the center of the circle. Okay, so this is the meaning of diametrically opposite. Now for each and every section on the diagram on the coil, there will be a point which is diametrically opposite, and because of that there will be a magnetic field in this direction as well. And if you see that the component along y-axis of this both magnetic field, they will cancel each other. They will be in the opposite direction, they will cancel each other. So only the x component of the magnetic field will be left. So we are interested in finding this x component of the magnetic field. So this is just the starting point. So dBx is basically dB sin theta, oh no, dB cos theta, sorry, dB cos theta, adjacent, right? Now what we have to do, we have to put the value of dB. Now how can we put the value of dB? To put the value of dB, we have to use Biot-Savart's law. If you remember, mu naught by 4 pi I dl sin theta. Now in that case, that sin theta, whatever theta was there, this is this angle theta, which is actually 90 degree. That angle between the dl vector and the distance vector, they are 90 degrees. So that's why, because it is a tangential direction, so it will always be 90 degree, and that ideal sin theta term, that sin theta term will not be over here. Okay, ideal by r square, okay, into cos theta. This cos theta is different than that ideal sin theta 1 theta. That theta is 90 degree. That theta will not come in this expression. Okay. Now, so from here we have to write mu naught by 4 pi, okay, I dl divided by r square. Instead of r square, what we will write? We will write r square plus x square, right? So this is r, so square of that means square root will be gone, right? Now cos theta, you have to put the value of cos theta. So what is the cos theta over here? So cos theta is basically this angle is theta, I said. So this angle theta means it will be r divided by small r, right? So r adjacent side, theta means, cos theta means adjacent side divided by the hypotenuse, that is square root of r square plus x square, right? Now let's put that value. So you will get mu naught by 4 pi IR dl divided by r square plus x square to the power 3 by 2. So r square plus x square into square root of r square plus x square is basically 3 by 2. So x into root x, that means x into x to the power of half. So it will be x to the power of 1 plus half, that is x to the power of 3 by 2. Simple mathematics. Simple mathematics, if you just do it, you will know this is nothing, not a rocket science. Now what? So we have done our homework. This is basically homework. Okay, now we will do the major operation. So Bx is basically if you take this all the sum of everything, okay, then you will get the total magnetic field, which is integration dBx. Now for that, here as you see that everything is constant, so everything is constant, so everything will be outside mu naught by 4 pi I r by even x is constant over here. Okay, x is also fixed distance, it is not changing, so that is also constant. Only thing which is changing over here is dl. Okay, now dl means what? Dl means you are taking small portions and you are adding it. So we already did it in our last derivation. So what is the meaning of that? It is nothing but mu naught by 4 pi I r divided by r square plus x square to the power 3 by 2 into 2 pi r. Okay, into 2 pi r. So basically the circumference of the circle, so 2 pi, one of them will be cancelled, and you can write this expression as bx equals to mu naught by 2 I r square divided by r square plus x square to the power of 3 by 2. Okay, so this is the derivation. Now there is one more addition to that. You can find the magnetic field due to the at the center. Okay, but that derivation is not required. This is the actual formula. You can close your derivation for this 5 marker question over here. This is the answer, and if you leave it here you will get the full marks. But in case they add one more term, that what will be the magnetic field at the center. For magnetic field at the center, okay, you must put x equals to 0. Okay, x equals to 0. So if you put x equals to 0 means this point will be shifted to the center, right? X is this distance. If you put x equals to 0, then you can calculate the magnetic field at the center. Nothing but you only have to put x equals to 0 over here, and in the denominator you will get r cube. In the numerator you have r square, so it will be cancelled and you will get mu naught I by 2r. That's it. Okay, simple, easy, no rocket science. So that will be mu naught I by 2r. How it came? Try it and let me know if you are able to solve it or not. Very easy. Next, derive the expression for force per unit length on two infinitely long thin parallel straight conductors carrying currents, and hence define ampere. Now this is also a kind of fixed question, especially in midterm exam. In midterm exam, this question is more commonly come than the other one, okay, because midterm question paper is set up by some examiners. They think that because the other one is coming year after year, so why not give this at least in the midterm exam. So that's why this question is more common in midterm exam. Okay, so that's why you have to practice this as well. So let us consider two parallel wires. So this one is wire number 1, this one is wire number 2. So current through this, say I1, current through this, say I2. Okay, the distance between them is, say, d. Okay, now what will happen? To find the force between them, we have to consider a fixed length initially. So the length, let us consider a length L of 2 wire. This is imagined. Okay, so this length is, you take a arbitrary length. Okay, this is arbitrary length L. Later on we have to divide this L so that we get a force per unit length, right? Now so the distance between them is d. Okay, the current is I1, this one is I2. Now what is the magnetic field? First what we will do, we will find the magnetic field due to wire 1 at a distance d. Okay, magnetic field due to a current carrying wire. Magnetic field due to a current carrying wire is given by magnetic field due to a current carrying wire 1 is given by mu naught I by 2 pi d, right? We did it for Ampere's circuit law, the derivation, 3 marker derivation, same magnetic field. So this is the magnetic field due to 1 at a distance d. At a distance d, who is located at a distance d? The second wire is located. Now because of this magnetic field, the second wire will experience a force. The second wire will experience as a force due to the wire 1's magnetic field. So this is why we have written it as F21. What will be that force? Force will be given by BIL. Okay, now here I will be I2 because we are measuring the force on the second wire, right? So now put the values, you will get mu naught I1 I2 by 2 pi d, okay, into L. So this is the force on the second wire due to first wire. Now if you exchange I1 and I2, if you exchange I1 and this is a symmetric equation, okay, so even if you exchange I1 and I2, location of I1 and I2, does it change any values? So if you write, say instead of writing this, if I write I2 first and I1 next, will there be any difference? Mathematically it will not be any difference, but if you just swap them, then it is basically the force due to the first wire due to second wire. Okay, now if you do the same method, that you calculate the magnetic field B2 due to the second wire at the location of first wire, and then apply the same principle and apply the same formula and calculate the magnetic force, basically you will see that the force will be same. Okay, so because this is symmetric, I1 and I2 only will change the position. I1 is coming first over here, in that case I2 will come first, I1 will be next, that's it. Okay, so basically magnitude wise they are same, direction wise they will be in the opposite direction. Okay, magnitude wise they both will be same, direction wise F21 will be negative of F12. Okay, the negative sign indicates from third law. Okay, now say this equals to common force F. Okay, because we are considering only magnitude. Okay, so magnitude means, let's say this is F. Okay, instead of writing F12, F3, F21, we are denoting it with the common symbol. So F is basically given by mu naught by 2 pi I1 I2 by d into L. Now this L is creating some difference, okay, because this L is arbitrary. It can be 1 meter, it can be 2 centimeter, it can be 10 centimeter, right? So what we have to do, we have to find the force per unit length, which is given by the force divided by the length, which is mu naught by 2 pi I1 I2 by d. This is the final expression, and if you do it you will get full marks. But there is one more, you have to define the ampere. So I have seen the same question was asked, student forgot to mention the definition of ampere. Now how to do that in case you forget? In case you forget the definition of ampere, you have to remember that you have to put everything as 1. Everything as 1. So if you put I1 I2 equals to 1 ampere, d equals to 1 meter, okay, then your force will become mu naught by 2 pi. Now mu naught by 4 pi is 10 to the power of minus 7, so mu naught by 2 pi will be 2 into 10 to the power of minus 7 Newton per meter. Okay, Newton per meter means because it's a force per unit length, so that's why Newton per meter. Okay, so now you have to add into the definition of the force. Ampere is the current when flows through each of the two parallel conductors kept at a distance 1 meter experiences 2 into 10 to the power of minus 7 Newton per meter force. Okay, this is the actual definition of ampere, right? Now let's move on to the next derivation. With the help of a diagram, derive the expression for the torque on a rectangular loop placed in an uniform magnetic field. Now this is not a 5-marker derivation, trust me, this is very easy derivation. It came once in the previous year paper, not in the first paper but in the second or third paper. second improvement. Previously there used to be improvement exam, now there is no such improvement exam. Previously it used to be only if you fail in the exam you can appear for the correction exam, but now you can appear for all the 3 exams. Improvement, they are calling it as improvement exams. Okay, even if you get low score and you want to improve it, you can appear for the second and third exam. Okay, previously it was not such a case. Previously it was only if you fail in the first exam, then only you will be able, you were eligible for the second exam. Okay, so one such paper, this question came as a 5 marker. Obviously because it's easy derivation, that's why it was given as 5 marker. Otherwise if it is coming to your paper, then most likely it will be coming as a 3 marker derivation. So here we have a loop which is basically carrying, say, a current I. Okay, loop means current is being carried like this. Now it is kept in an external magnetic field. Okay, it is kept in an external magnetic field, say B. Okay, now what will happen? So if you are keeping the current carrying loop in the external magnetic field B, it will experience as a torque. So you have to find the expression for the torque. So for that you have to first check the dimension of the loop. So this, say, length is L. Okay, breadth, say, B. Okay, length, say, L, breadth, say, B. Okay, now what? So external field is B. It is a current carrying wire, okay, of length L, kept in a magnetic field B. So what will be the force acting on this arm? Force acting on this arm will be L cross B. So L cross B, so it will be into the paper, okay, into the paper, and for this it will be L cross B, so it will be out of the paper. Okay, one will be into the paper, one will be out of the paper. So what is the force acting on it? Each of them, both will have the same amount of force, only difference is one into the paper, one is out of the paper. Okay, so what will be the force? Force is given by B I L. Sin theta is 90 degrees, so sin theta is 1. Okay, this is the force, any one of the force. Okay, F, both forces are F. Okay, now two equal and opposite forces acting on an object, so that means it will, if the force is uniform, magnetic field is uniform, definitely it will give you a torque. Okay, and what is the expression for torque? Torque is given by force into the distance. Distance means distance between the forces. Okay, so distance between the forces is basically the torque. So F into B is the torque. Now F, put the value of F, B I L into B. Okay, now B I L into B. What is L into B? L is what? L is length. B is what? B is breadth. So length into breadth is what? Length into breadth basically gives you the area of a rectangle, right? So length into breadth gives you the area of the rectangle, so it will be B I A. Here A is the area, right? Now here we have considered only one loop. In case we have n number of turns, then it can be written as tau equals to NBIA. Okay, so this is the expression for torque. Very simple, easy derivation. This is not a 5 marker derivation. Okay, just step by step if you do, most of the torque derivations are actually 3 marker. This will also be a 3 marker. Now this is a new question that added in your last year's model paper. So that's why I have included this in this session as well. In case some of the districts may choose to follow the last year's model paper, then they may give you this question. So be prepared, easy question, not a difficult one. So that's why don't worry too much. Only this diagram you have to practice. There is a simplified version of this diagram, you can check that out in internet, but otherwise this also is not a super difficult diagram. What is the principle behind the working of a moving coil galvanometer? With the help of a neat level diagram, obtain the expression for the angular deflection produced in moving coil galvanometer. Principle: when a current carrying coil is placed in a uniform magnetic field, it experiences a torque. That means the principle is basically the previous one. Okay, so what is the expression for the torque? Torque was given by NBIA. So this is the basically principle of working of a galvanometer, right? Now we know that if we attach a spring, okay, if we attach a spring to this coil, then there will be a restoring torque. Restoring torque means it will try to prevent any more rotation of the needle. Okay, so the restoring torque, if the angle that it makes, okay, is given by theta, then not this angle, this angle, yes, because galvanometer generally at rest, galvanometer generally points at this 0 direction. Okay, so galvanometer generally rests like this, it points, this is 0. So if it is rotating like this, this will be theta. Okay, so this is called the angle of deflection. Okay, now the restoring torque that is generated can be given by torque equals to the constant of spring constant times the angle of rotation. Okay, the angle of deflection. Okay, so here K is called the spring constant, there is a spring used, so this is the restoring torque. Okay, now put the values. NBIA equals to K into theta, or theta equals to NBA by K into I. Okay, or theta equals to G into I. So basically G is called galvanometer constant. G is called galvanometer constant, which is NBA by K. Right, so this is a very simple, another easy derivation. Only the diagram part is little tricky, and the principle was also very easy. Otherwise the derivation is very simple. Now if you like this video, don't forget to give it a thumbs up, and obviously share it with your friends. And if you have not yet subscribed, definitely I wish you to subscribe to our channel. Subscription is very important for our growth, and that inspires us to make more such videos in future. I'll be back with a new chapter very soon. Till then, bye.